So in our 490, 491 folder, we're going to go to our Unit 1 notes, and I'm going to scroll to where we left off in our last class. And we were talking about these transformations, just like we just did on the Kahoots. Okay, moving up, down, left, and right. And we had all these parent functions that we were applying those rules to. So what I want to do now is the last section is on inverse functions. Now, let me perhaps explain it like this. When we first began talking about functions, we might have had a function like this, where let's say this is our function box. Remember, f of x is, let's say 3x plus 1. All right, so this is our function. And what we're going to do is we're going to drop in numbers. So I'll just pick an easy number here. That's our input, which is our x value, which is in our domain. All right, what's it going to spit out?
7.
It's going to spit out a 7, right? So, and that 7 is an output or a y value, which is in our range. So I think we have that concept down. And we also did a composite function where then that 7 then dropped into another function. But we're going to change it just a little bit today. Now I want 7 to drop into another function so that I end up right back where I started. So following the path, we're going to drop 2 into here. It's going to do that to it, spit out a 7, which is going to go into here and do something, and finally get us back to our original 2. So basically, this function here has to undo what that function did. Well, if we think about what happened in this function, we multiplied by 3 and added 1. So if we had in this function, if we took the number and subtracted 1 and then divided by 3, so if we did 7 minus 1, which is 6, divided by 3, that would get us back to 2. Well, when that happens, that's called an inverse function. And it's denoted like this. It has f and a little -1 of x. So we would say the inverse of f. And the nice thing about functions and inverses is that they work for any number. So I'll pick another number out of the air. 8, okay? So it comes into the first function. 8 times 3 is 24, plus 1 is 25. Then that 25 is going to drop into this function. So subtract 1 is 24, divided by 3 is 8. We get back to where we started. So whatever is happening inside of this function here is being undone in this function here. That's what an inverse function does. Is it kind of undoes all the rules of the regular function, and vice versa for that matter. All right, so in this case, if we wanted to find the inverse function, if our function was 4 times x, well, how do you undo 4 times x? Instead of multiplying by 4, you divide by 4. So our inverse of f would be x divided by 4. So it has to undo what the original function did. Now they're going to get a little harder, so stick with me here. In the next one, in part B, if we had f of x is 1/5 times x, so it's 1/5 times x, then we're going to divide by 1/5, and dividing by 1/5 is the same as multiplying by 5. So its inverse would be 5x. All right, so to do the next one, you know, this one was a little harder. The next one gets a little harder too. And some of you might be able to do this in your head, but some of you probably can't. And that's okay, because I'm going to give you a method. So in this case, our function, we put something in for x, it's going to multiply by -3 and add it to 5 and then divide it by 2. And to undo all that in your head might be a lot. So here is a method that we can use to solve for our function. You know, f of x is a lot like y. So think of it as y. So if it was y equals 5 minus 3x over 2, and then we switch x and y. So instead of that y, I'm going to make it x. Instead of this x, I'm going to make it y. So it's going to be 5 minus 3y over 2. So we switch for x and y, and then we switch x and y, and then we're going to solve for y. So I multiply both sides by 2. I get 2x equals 5 minus 3y. Subtracting the 5 over, I have 2x minus 5 is equal to -3y. And then dividing by -3, I have 2x minus 5 all over -3. That is our inverse. So we switched the x's and y's and solved it for y. Now the proper way to denote that would be, we would say the f inverse of x is this thing, is -2x minus 5 over -3. All right, if you have any questions, please just ask. Well, when we did our inverse model up here, remember we said we could put anything into the first function, it's going to spit something out, and no matter what, it will always give us the same thing we started with. It's always going to get us back to where we started. Well, anything in math we often call x, because x is a variable. It could vary and be different things. So let's kind of follow that. If we dropped x into the first function, it's going to spit out 3x plus 1. Then when 3x plus 1 drops into here, you get 3x plus 1 minus 1, which is 3x over 3, which is just x. So again, we get back to where we started from. So in that case, we can put in any x and we should get out an x at the end. So let me go back down to our example. And before we move on, I did have a question of how did 2x become negative? Oh, I made a mistake. I wrote a negative and I shouldn't have. Thank you. That 2x is positive from here. Thank you. Sorry about that. So thanks for pointing that out. Please, I know sometimes when I talk and write, it is possible, of course, to make mistakes, and I appreciate you guys pointing those out. All right, so if we want to show that functions are inverses, here's how we show it. We have to show that f of g of x equals x, and that g of f of x equals x. Now, here are our two functions. So the first thing we're going to do is find f of g of x. So that means we have to take g of x and plug it into f. We have to take this function and we're going to plug it in to there. So we're finding f of this whole thing. And I really should say that. The cube root of x plus 1 over 2. So we have to take that function and plug it into f. Well, when we do that, we get 2 and then times, so I'm plugging it into here for x. 2 times the cube root of x plus 1 over 2 cubed, and then minus 1. And we want to simplify that. Well, when you simplify that, you have a cube root of something cubed. Those two operations cancel each other out. And we have 2 times x plus 1 over 2 minus 1, because the cube root and the cube cancel each other out. So our 2's cancel and we have x plus 1 minus 1, which of course equals x. So we have shown that f of g of x equals x. Now we're halfway home. We got to do the other half. We still have to show g of f of x equals x. So I have to find g of f of x. So that means I'm going to take this guy now and plug it in to there. So I'm finding g of 2x cubed minus 1. Okay, so I'm plugging 2x cubed minus 1 into g. So that's going to be the cube root of 2x cubed minus 1 plus 1 all over 2. Well, when we're simplifying that, we have minus 1 plus 1. Those guys are going to cancel out. So we have the cube root of 2x cubed over 2 which is going to be the cube root of x cubed, because the 2's cancel. And then that's just x. And so we could say these 3 little dots in math language means therefore, used in proofs quite a bit. Therefore, f and g are inverses. Okay, we showed that f of g of x equals x and g of f of x equals x. So graphically what happens, it's asking us to use a graphing utility, and we're going to graph these 2 functions. So I got to write them down because I didn't write them down. So we have 2x cubed minus 1 is going to be our first function. And then the cube root of x plus 1 over 2 will be our second function. I'm going to graph those on my graphing calculator. So I'll open up my Inspire and I'll go to a new graph. And I'm just typing in the function. So 2x cubed minus 1 that's our first graph. And now I'm going to type in my second graph, the cube root of x plus 1 over 2 I'm sorry, I meant to put them both on the same graph. To do that, you hit the plus sign in the upper right corner. My mistake, I hit the add in the upper left corner. So I have to type in the 2x cubed again, minus 1, so that they're both on the same graph. I just wanted you guys to be able to see them both on the same graph. And the reason I wanted you to see them on the same graph is because they are actually a reflection of each other. They're a reflection over the line y equals x. So if you can visualize that red graph and the black graph are reflections of each other over the purple graph. And remember, the red graph and the red graph, those are inverses. Inverse functions are reflections over the line y equals x.
How do you do this on a regular calculator?
Let me pull that up at the end and I'll show you on, because it takes a long time for that app to open, but I'll start opening it now and I will come back to it, okay?
Okay, thank you.
Yep. But the idea that they, I really wanted you to see the visual of them being reflections over the line y equals x. Now, the reason that's important is because of what's called a one-to-one function. The horizontal line test is just like the vertical line test. You use the horizontal line test to show if a function is one-to-one. So for example, this function right here is not a one-to-one function. It doesn't pass the horizontal line test. Now, why that's important is because if we took that parabola and reflected it over the line y equals x, its reflection would look like that. And of course, that orange function, that orange graph, is not a function. It doesn't pass the vertical line test. So what the horizontal line test does is it tells us if a function is one-to-one. But basically it tells us that if you have a function and it's not one-to-one, then its inverse will not be a function. However, if you have a function that is one-to-one, so for example, if we had the graph of the square root of x, okay, that is a one-to-one function, passes both the horizontal and the vertical line test. Well, when we reflect that over the line y equals x, its reflection is also a function. So if it's one-to-one, the function and its inverse are also functions. So down here at the bottom, we want to complete the table for the inverse. Now this is the function. We're not completing the table for the function. We're completing the table for the inverse. So let me go back to our original demonstration here. And one thing that I want to point out here is that this is the domain of the function, and that becomes the range or output of the inverse. So the domain of the function is the range of the inverse. And the range of the function is the domain of the inverse. So what happens is, remember, domains are x's and ranges are y's. So if you have a function with an x and a y value, the x and y value of the functions switch position to be the x and y of their inverse. So when you have an inverse, the x's and the y's switch. So for example, the coordinates of this point, I'm going to write down the coordinates. This is on the function. This is the point 3, 3. This is the point, this point here is the point 1, 2. This point is -1, -2. And this is the point -2, -4. So that means for like this point here, that means for an input of -2, the output is -4. What that means on its inverse is for an input of -4, the output is -2. So on the inverse, an input of -4, its output is -2. Just like looking at this point, for an input of -1, its output is -2 on the function. On its inverse, for an input of -2, its output is -1. So you're switching the x and y values from these are the x, y values on the function. So they switch on its inverse. Just like the first one, these were the x and y values on the function. They switch on the inverse. So these two are going to switch, meaning 2, 1 is going to be on its inverse. These two switch, but of course that doesn't matter because you still get 3, 3. But notice if I were to plot those points, we have, so -4, -2 is here. And -2, -1 is here. And 2, 1 is here. And 3, 3 is there. If I connected those points, the green graph is the inverse of the black graph. And notice graphically, they are a reflection over the line y equals x. All right, so again, to recap, we started off with the idea that given a function, its inverse undoes all of the things that are happening inside the function. And because of that, you end up right back where you started. Or another way to say that is the domain of the function becomes the range of its inverse. And here, that's the range of the function, which is the domain of its inverse. So one method for finding what an inverse is to set y equal to that, switch the x's into y's, and solve for y. A way to prove that is to show that f of g of x equals x and g of f of x equals x. And then we looked at it graphically on our graphing calculator, showing that a function and its inverse are a reflection over the line y equals x. And then we took some coordinates to graph that to show that it is a reflection over the line y equals x. And that ties into the horizontal line test. The horizontal line test is used to determine if a function is one-to-one. Because like in this case, if it doesn't pass the horizontal line test, then its inverse is not a function. But in this case, if it does pass the horizontal line test, then its inverse is a function. All right, so I threw a lot at you there with inverses and functions. Any questions before I move on to something else?
I'm kind of confused on the F and the G example you did.
Say that again, please. Which part?
A function of x and then g of x. Show the functions are inverses of each other.
Yeah, here to show their inverses.
Yeah, could you like explain what you did real quick? I was kind of confused on the second part.
Sure. You have to, so to show if they're inverses, you have to find f of g of x and have to show that it equals x. So, and then you also have to find g of f of x and show that it equals x. So for example, here, if I wanted to show that these two were inverses of each other, I would find f of g of x. So I'm finding that composite function, which means I'm going to take g of x, that, and I have to find f of that thing. Okay, f of the fifth root of x. So I'm going to be plugging that into f. So when you do that, plug it into there for the x, we get the fifth root of x to the fifth power, because it's the fifth root of x to the fifth power. And when you have a root and a power that are the same, those two operations cancel each other out. So we found f of g of x and showed that it equals x. We now have to do the same thing, show that g of f of x also equals x. So that means we're going to take f of x, that guy, and plug it into g. So we're finding g of x to the fifth, because that's f of x. So that means we're plugging x to the fifth into there. So we have the fifth root of x to the fifth. Well, again, you have x to the fifth and the fifth root. Those two operations cancel each other out. And that also equals x. So we have shown that f of g of x and g of f of x both equal x. Therefore, f and g are inverses. So the nice thing is, if it tells you they're inverses, we know it comes out to be x. We just have to show the algebra so that it supports that.
What do those three dots mean?
I'm sorry?
What do those three dots mean?
That means therefore.
Okay.
Yeah, it's just shorthand for therefore.
Do we need to write it like that if we're going to do it?
You could write out the word, that's fine.
Okay. Or can we just say yes, they are inverses or no?
Yeah, that would be fine.
Okay, thank you.
Yep. All right, good questions, guys.